So all in all, I was not unhappy with the exam. Thank you. If you've got questions, I posted the key last night after I finished the grading. Please read it over, then come talk to me. I will happily discuss questions. The average is better than exam 2. I'm very happy to see that. But you will see these things again. I want to continue looking at our differential equations. So I want to start with an example. Now, my first reaction upon seeing this is that I am not in the same situation we were on Monday. Because on Monday, I had y prime, and then everything on the other side was just x. So I could integrate. Here I can't do that. This is not set up in a method where I can just integrate. I don't have y prime away from y. It's not explicitly given just in terms of x. So rather than actually trying to solve this right away, I'm going to try and understand what's going on sort of a little more heuristically. What can I do that doesn't involve me solving this, that still allows me to figure out what's going on? So, let's see if I can figure out some properties of the equation that would satisfy this differential equation. Okay. Now, eventually I will go on to solve it, but for the moment, I'm not going to. I'm going to do all of this examination without actually solving it. And I think to myself, I know something about y prime. I'm going to go back to Calc 1, to Chapter 3, as a matter of fact, a long time ago, and I'm going to think about this idea of linear approximations. If I know the slope, I know how far over and up I move as I move to the right or the left. I can get rise over run. I can draw a picture of a straight line that in a small neighborhood is the tangent line to my curve. Okay, this time, y prime depends on both x and y, not just x. So let's take the Cartesian plane. And let's pick some points. And at each point, I want to evaluate y prime. So somebody pick a point on the xy plane. 1, 1. At the point 1, 1, well, I know that y prime equals x plus y. That's 1 plus 1, that's 2. So if I were going to draw a straight line here, I would want it to have a slope of 2. But I know that that particular straight line is only the right tangent line in a very small area around x equals 1, y equals 1. So I just draw this little piece of a line. I'm going to do this everywhere. If I go to the point 1, 0, I'll get a slope of line 1, line of slope 1. If I go to the point 1, 2, I'll get a line whose slope is 3. If I go to the point 0, 1, I'll get a slope of 1. If I go to the point 0, 0, get a slope of 0. But I also get a slope of 0 at the point negative 1, 1. Now, this is a pain in the neck for me to keep doing by hand. So I'm going to cheat. On our Canvas page, there is a movie, a screen recording of me doing what I'm about to do for you right now. So, in my MacBook, I am going to open up the Mac Grapher. If you go to the Launch pad and open your Utilities or Other section, it's this thing that looks like a waterfall. Here in my picture, it's the top center. That colored waterfall grapher. I opened that up. And it brings up, typically it brings up a choose. So let me do it again. It brings up this and allows me to pick what format I want the axes to look like. I can have axes in the middle like normal. I can have them on the edges. I can have no axes that are really emphasized and all the marks are on the outside edge. I'm just going to go with this default behavior. That looks like a normal sheet of graph paper. This allows me to graph anything. Explicit equations, implicit equations, whatever I want to graph. This cannot be done on the graphing calculator, unfortunately. The graphing calculator won't do this piece. I want to assign to every point on this screen a little arrow. And the arrow is going to have the slope here that we've created. So to do that, I need to tell it, let me clear out this equation, that the change in x and y is given by our slope. Change. Chemistry. Change. What's the symbol for change? And it's a capital delta. So I'm going to type the word capital D-E-L-T-A, and as soon as I type A, it turns into delta. Then I want to give it x and y like a point. But because I'm thinking of this like a vector, vectors were trig in physics and a long time ago, I go over to this little sigma here over on the right. There's a little down arrow menu option there. If I click on that, there's a two-dimensional column. I'm going to click on that sucker. That says change in x and y. I want our slope, right? Our slope is dy dx. Well, delta y delta x, right? So I'm going to put delta x on the top and delta y on the bottom. But the equation I have for my slope is this. That's a fraction. What's the denominator of that fraction? 1. So that's change in y, and my change in x is 1. So I go back to the grapher, and I say I want another ordered column, and the change in x is going to be 1, and the change in y is going to be x plus y. When I do that, it will draw all those little arrows for me. And they're even rainbow colored. That drives me crazy. I don't like doing this in rainbow colors. You can change the colors if you want with the inspector by setting it up to not use different colors, and then they're all the same color. Yes, Leo? You cannot. This is not doable on the graphing calculator. That's important, but that's why this is built into your MacBook. and why I recorded this, why this recording is on our Canvas page. So you can see how to do this, so you don't have to draw these things by hand, because I could print this picture. Now I will go and say I could also do this in slopes. Remember I told you there was that app on my iPad or my phone that we're linked to called Slopes. Slopes. And if I open that, the problem is that Slopes doesn't do X, it does T. But if I type in y prime equals t plus y, it draws the exact same picture. The very first one, the default. Again, you're probably best off watching that movie and keeping some good notes. If you're trying to do this on the calculator, you're not going to be able to. But here's the interesting part. Having this picture now allows me to say, if I draw a curve that's the graph of the function that obeys this, these should be tangent lines. The point you picked, Jacob, was 1, 1, right? So if I go through the point 1, 1, that's right here, based on my scale, I can go, I want to go through that spot. And notice how it follows the arrows. Those are tangent lines to my curve as we go to the right. Now, I didn't actually hit 1, 1 all that precisely, but I could go in and fix that to be exactly 1 for each of those. Now that goes through the point 1, 1. Perfect. I don't know what the equation of that curve is. Do you? I have no way of knowing what the equation of that curve is. But it turns out that no matter what starting point I pick, let's say I pick the point 0.5. Well, there. I see a very similar sort of behavior, don't you? But if I pick the point that's over here, say 0, negative a quarter, that stretches out pretty well too. Oh, wait a second, something different happened. Kind of hard to see, but that's going to go in a different direction. Oh, how interesting. So there's some sort of division here between curves that will eventually curve back up and curves that will curve down. And if I touch different places on the y-axis, some of them go up and some of them go down. But I didn't need to solve the equation to do this. All I did was on this program say, follow the arrows. I can't do that from here with any other idea other than trying to do it by hand. I could kind of attempt to draw a curve that follows these arrows. And in our textbook, they will actually ask you to do that. They'll give you a picture. The picture we came up with is called a slope field. And when you open the app, Slopes, it gives you several options, the first of which is slope fields. So that was where I was to write the equation t plus y to get the picture we were looking at. Come on, white balance out again on me. This, though, is an example from, I didn't just make it up for shits and giggles. This is example 1, page 592. There's the slope field in figure 3. They drew it at every point. And then in figure 4, they just kind of, I want to go through the point 0, 1. As I go towards the right, I will follow these arrows. As I back up towards the left, I will follow the arrows. So I can do that for any picture. This one's equally disgusting. Look at that. It's all twisty in the middle, right? So if I start to draw a picture, I'm going to weave back and forth. But this is for the differential equation, y prime equals x squared plus y squared minus 1. Wait a minute, x squared plus y squared minus 1. That sounds like my unit circle. It makes sense that there's this sort of circular weirdness in the middle here. And some curves go up, some come back down. There's all sorts of interesting stuff going on here. And I can simply kind of ad-lib a picture this way. I'm going to steal a problem from physics lab. This is a lamp with an electric source, E, a battery, a plug, whatever it is, a resistor, R, and a load, L, the lamp. It's usually illustrated, the resistors are illustrated as this sort of jagged behavior because they slow electricity down. It's hard to make those sharp corners. The load, L, looks like the filament in an incandescent light bulb because that uses the electricity up. Well, it turns out that there's a differential equation that relates I is current, E, if that's a battery, you measure batteries in what? Say again? Volts. That's voltage. Current is measured in, this is the thing I don't like about the physics of electricity. Everything's named after people. Unfortunately, no, joules measures energy. Current is measured in amps. For ampere, this is a version of what is called Ohm's law. And resistors are measured in ohms. Again, people. I was actually talking with the physics teacher a couple weeks ago, and I said, that's the problem. In kinetics, in physics 1, it's all grams and meters, and it's based off of stuff. In physics 2 and electricity, it's all named after people. I can never remember who the hell is who. Electric charge is named after Coulomb. Joules for energy, I give watts. So what? Well, it's James. James was busy. He came up with this stuff. But this is a differential equation. And this differential equation can be written y prime equals stuff. If I think of I as a function and di dt as its derivative, I can write I prime plus r over L I equals, you just said batteries are in volts, right? So like a 12-volt battery, a 9-volt battery, a bunch of batteries squeezed together, I can make a 60-volt battery cell, like in a Tesla. I can do all sorts of battery behavior. which means if I move that to the other side, I have an equation that looks like this. Oh, I forgot. Load. Load needs a unit too. L. L needs a unit. Again, it's named after people. Load is measured in henries. That's who they were. That's who discovered and then put forward these ideas. So let me put some numbers to this. Let me suppose that I have, oh, I forgot I divided everything by L. This gets divided by L also. If I divide by L, I have to divide by L everywhere. Let's suppose I have a battery of 60 volts, a resistor of 12 ohms, capital omega for ohms, ohms, O-H-M, ohms, and a load of 4 henries. By the way, this makes units drive me nuts in electricity. Batteries in volts I get. Resistors are marked in ohms. Light bulbs are not marked in henries. How the hell do you figure out the load issue on a light bulb? You actually have to do an experiment. Unless it's marked somewhere, and you will never find it on anything other than the spec data sheet that comes with the package of light bulbs that almost everybody throws out. So if I set this up, what do I get for my differential equation? Now this is interesting to me because as opposed to the equations we were doing Monday or the one I was just doing, this time on the right-hand side of that equation, there's no x, there's no t. If I were to write this in y and x, it would be y prime equals 15 minus 3y. This doesn't care what x is, it only cares what the value of y is. Which means, if I were to try and draw a picture for this, a slope field, and I ask you to pick a point, somebody pick a point. Okay, if I do 1, 1 again, when I put in 1, 1, I really only care about the y value being 1, right? So when y is 1, I get a value of I prime equals 12. Yes? That's a pretty steep slope, isn't it? That's going up pretty fast. But here's another interesting comment. As long as I keep the y value the same, whether I move to the right or the left, that slope won't change, will it? As a matter of fact, every x value at a height of 1 gets this exact same slope. At 2, 3, 4, 5, 6. I can do the same thing. But all of the lines at any fixed height are the same. What's the slope at a height of 2? Okay, so that's a little less steep. And at a height of 3, it's a little less steep. And at a height of 4, it's a little less steep. What is it at a height of 5? Oh. What is it at 6? Negative. Now, what's interesting, this type of phenomenon is so interesting and so useful, it gets its own name. Since the right-hand side doesn't contain any of the independent variable, there's no t, there's no x, we call this an autonomous differential equation. These are a lot easier to draw the slope fields for. As a matter of fact, I'm going to go into Grapher and change our picture. I want it to be y prime, the left side, that's dy dx. Change in x is 1, the change in y is 15 minus 3y. Now, it's kind of hard to see here. Let me change it back to all be in one color. And if I zoom out, look at that. At 5, we've gone from going up to going down. Need to move this rather than point. No matter how far to the left or the right, the arrows all look the same. And as I get closer and closer vertically to 5, all of a sudden they go straight across, aren't they? So I said this was a lamp and a battery, right? How much current is moving through the lamp? In this picture? None. Switch is open, right? Hey, I didn't throw the switch. You close the switch, what happens? I hope so. Otherwise, I have broken wiring or a bad battery or a bad light bulb. The electricity should start moving, right? Moving electricity, that's what current is. That's what our slope field represents. This picture tells me the change in current at any given time. So if the switch is open and I go, okay, throw the switch at time 0, how much electricity is moving? I haven't done anything yet, right? So at time 0, there's no electricity moving. As soon as I throw the switch, the electricity starts to move. So we would be going through the point 0, 0. What's going to happen? But as it goes up, it starts to flatten out. And eventually, the current starts to be in equilibrium. The light comes on and then stays on. And it stays with the same brightness because the electricity is moving through it at a constant or near constant rate across that top. That's where my derivative is 0. What did we call that on Monday? I'm sorry, say again? A particular solution is something we get when we actually solve it. Haven't solved the equation yet, but I gave this idea a name. Back when we were talking about our population growing and our way back at the beginning of Monday's lecture. I sure as hell hope I used this word. We called it an equilibrium. And because we're getting closer to it, we called it a stable equilibrium. Great. I still haven't solved this equation. I don't know what the actual values are. I can kind of guess by plotting a curve, right? But if I can kind of guess by plotting a curve, I can do the math behind those guesses. I did not develop this. I'm going to use our linear approximations. Okay, at time 0, we know that the current is 0. I would like to know what the current is at time 1. Now, I could do a linear approximation. How do I do a linear approximation again? Hint. Think Taylor series.
It'd be like x raised to the end of a and x squared s minus a to the end.
That's my Taylor series, but I'm saying I want a line, right? What's the highest power in the equation for line?
One.
So let's use the Taylor idea, but let's only use 0 and 1 for n. I'm going to come up with a straight line. So I use f of 0 plus f prime of 0 over 1 factorial. I'm sorry, 1 factorial is just 1. X minus 0 to the 1. But I know this number. That's right here. How do I find that number? in our particular example, using I. My derivative is I prime. How do I find I prime? I can use this equation to find the slope because I'm at the point 0, 0. So I take that y value and that x value and I plug them in. And I get a slope. My linear approximation is 0 plus 15x. So at the point 0, 0, ready? I'm going to go back to the slope field picture. At the point 0, 0, there should be a line of slope 15. So I throw the switch, we move over a bit, follow the line. Now here's where the process gets interesting. You get to decide. Remember, my goal is to figure out what the actual current is at time 1. How many steps do you want to take to get to 1? You could just say, we'll do it in 1 step, right? If I take 1 step, my new x value is 1, right? According to my equation, what's my y value? What do you get for current? If you take this equation and plug in 1. No, I'm not plugging it in here. I'm plugging it in here to the line we just found. Aha! But either way, that doesn't make sense to me, does it? Because if I look at that picture, we should stop by 5, shouldn't we? So that seems like too big a story to follow. I don't like that. All right. So maybe that's too big of a step. I'm going to change my idea then. Let's take fewer steps. Sorry, more steps, each one being small. Take a step of a smaller distance. I know I was going down somewhere. I'm going to take a smaller step. Change in y is the old y, let me write it this way. Y new is y old plus slope times change in x, right? Change in y over change in x is slope. So how many steps do you want to take to get from 0 to 1? I'm going to take more than 1. Let's take 5. Taking 5 steps. I'm back to Chapter 7, I'm back to chapter 5 last semester. What's delta x? Going from 0 to 1 in 5 steps. Integration. Midpoint rule, Riemann sums, Simpson's rule, all that crap. How do I get delta x? N is 5. I said I'm taking 5 steps. N is 5 to do on the top of that fraction. Y'all took the first exam. It's on the formula sheets for the first exam. It's b minus a over n. We take the two ends of our ranges, right? So my delta x is 0.2. So here's what I do instead of using 1. I start at the point 0, 0. When you throw the switch, there's no electricity, time starts. I say, okay, to get the next value, the new value, I take the old value and I take the slope at the old values. I put in x old and y old. And then I multiply by delta x. Okay, wait a minute. That's 0 plus something times 0.2. And Leo, this is where I get to use the I prime equation. I use 15 minus 3i. What's the value that goes in there?
12.
Oh, no, the value that goes here. It would be the I that was found here. So 0. Oh, so this is 0 plus 15 times 0.2, which is 3. Okay, wait a minute. At the point 0, 0, there should be a line of slope 15. This time delta x wasn't 1, it was 0.2. So you go up to 15, and went up to 3. That's a better idea. That's step 1. I have to take 4 more steps. I2 is I1 plus f prime of times 0.2. This time, x is 0.2, y is 3. Huh? Why did those change? Oh, we moved over a step. This is my new I, and we took 1 step, so I have a new t, and that's where those numbers come from right here. Wait a minute, so that's 3 plus 15 minus 3 times 3 times another step. 15 minus 3 is, 15 minus 9 is 6. 6 times 0.2 is 1.2. That's 4.2. This is my new I. My new t, I took a second step, so I'm now at 0.4. What's I3? Okay, it's my new I, 4.2 plus 15 minus 3 times something times 0.2. What number goes here? It would be the 4.2. So that's 4.2 plus, what is this number after I do the subtraction? 2.6 times 0.2? 2.4? Yes, 2.4. Times 0.2, so that's 4.2 plus 0.48, that's 4.68. And that's my I, and my new T is 0.6. I'm going to do this 2 more times. And eventually I'm going to get to where I want to go, right? I'm going to get a value for T equals 1. This is just doing the same slope calculation over and over and over and over again, isn't it? I'm doing the same thing a million times. I should write a piece of computer code for this. So I did. And I cheated. I wrote it in the computer language for the TI. And I put the program on our Canvas page. You can go get that. And then you can use the USB port on your calculator to move it from your computer to your calculator. It's a program called TI Connect. It's available at the Texas Instruments website. It connects your calculator to your computer. And then this little 2-headed arrow thing, that's the TI Connect program. You can get that and download it. And then you can take the program that you download to your computer and shove it on here. You could, but in order to create it straight on your calculator, you have to input all of that. And if you want to, you can go to the programming manual, which is in the online manual for this, and you can learn where all of the commands are, because display and prompt are in different places on here. But you could type this in. But I already did that. So I'm going to cheat, and I'm going to do program. I have a lot of programs on here, but way down here is the Euler program, and I'm going to edit that program. I'm going to edit this line, the line that has the K in it. So when I edit this line, I go down and down and down and down and down and down until I get to that thing that says 4. There's the line I want. I'm going to change that to look like our function. 15 minus 3 times y. There we go. I was using I, right? Well, the calculator is stupid. It only uses y and t. As a matter of fact, that's why I wrote it to the function t and y. So I need to make sure that my x value, my t value, and my output value is always a y in this setup. But now I have this program. Quit. And I'm going to run that program. Run it. Make sure you put the function in the right place. I did that. Hit enter. Where am I starting? I'm starting when t is 0. My starting y value started when y was 0. How many steps? 5 steps. How big is each step? 0.2. That's h. F of x plus h minus f of x. That's why they call it h. Aha. There's my first step. New t, new y. Didn't we get 3 for the first step? What did we get for the second step? Third step. Fourth step. Fifth step. Made it. I don't have to solve the equation. I I can still tell you what's going on as time marches on. It is worth doing this by hand at least once to try and understand what's going on. I'm much more of the opinion that if you want to do this, you should put this program in your calculator. Euler's method, because that's what this devolves to, is a method developed by Leonhard Euler, is also available within slopes as well. If I go back to the main menu, there's some section called methods, and methods allows me to do Euler's method. I'm not going to do that on here, and there are a large number of other numerical methods for solving differential equations that I will put off to the differential equations course. So moving forward from here, my goal is to figure out how to solve these. I'd like to know exactly what function we were just finding points on. What's the graph of the right thing? But that's what we'll do. Not tomorrow. Tomorrow, question and answer for 9.1 and 9.2. I'll see you all. Have a wonderful rest of your day. By the way, after you get to the last one, if you hit enter again, it says I'm done.